I will derive the Lorentz contraction. Let us have two inertial systems. One which we call K, which is in rest, and the other called K primed, which is moving with a velocity y in this direction. And we prime the axis x and y primed and x and y here. Now we have a light clock with the length of L0. If we put this light clock in the direction of movement, then this length could be different, measured in the two systems. But if you put this light clock perpendicular to the movement, it can be shown that the length will be the same in these two systems. But let us have a light clock aligned in the direction of movement. We know that a clock will show different time in these two systems. A time interval here will, which is defined by a clock which is moving with this system, will appear different in this system. And this is the time dilation. So a time interval in a system where a clock is moving divided by the time interval where the clock is in rest, as here, is 1 over the square root of 1 minus u squared divided by c squared. And the time interval is defined by the time it takes for a light pulse to go from the emitter, be reflected back of the mirror and back to the emitter. In this system, this time interval t1 prime plus t2 primed is equal to the length it has to go, forth and back, 2L naught divided by the speed of light. But it will be quite different in this system, because the speed of light will be the same in the two systems, but the length light has to go is different in these two systems. If we start the clock in this system when the light pulse is emitted, stop it when it is reflected, it has to travel a longer distance because the whole system is moving with a speed of u. So it has moved this distance under the time the light pulse is going from the emitter to the reflector. So it has to go a longer distance. The total distance this light pulse has to go, measured in this system, will be ut1 plus L RL. And this will be, because velocity of light, the speed of light is the same in the two systems, this will be c times t1. Length divided by the time is the speed. And then this light pulse has to go back. But under this time, which we call t2, the whole system has moved distance u t2, so the length is smaller. It has to go L RL. This length measured in this system minus u t2. And this is c t2. From this we get a time interval measured in this system, t1 plus t2 equal to t1 is L parallel divided by c minus u T2 is L parallel divided by C plus U. And this will be L parallel times C plus U plus L parallel times C minus U divided by C squared minus U squared due to the rule of conjugate. And this will be L parallel C plus L parallel C, it's 2 L parallel C, L parallel U minus L parallel U is 0. This will be C squared minus U squared. And now we use this relation and this relation to see the relation between the lengths in these two systems. The length of the light clock in this system, where the light clock is in rest, and the same length in this system, measured in this system. Delta T is T1 plus T2, and this will be 2L parallel C divided by C squared minus U squared, and T prime will be 2L naught divided by C, 2L naught divided by C. Now this will be L parallel divided by L naught times 1 minus U squared divided by C squared. And this is equal to 1 over the square root of 1 minus U squared C squared. 1 over 1 minus U squared C squared. So the length measured in the system where the clock is moving will be equal to the length measured in the system where the clock is in rest times the square root of 1 minus U squared C squared. And this is the Lorentz contraction. When we have a ruler, for example, instead here, it will contract by this factor. It will be smaller measured in this system by the factor 1, the square root of 1 minus U squared C squared.